this is section 3.9, which is where this textbook actually introduces the derivatives of exponentials and logarithmic functions. We've already introduced the derivative of the exponential, so we'll go very quickly through that part. But then we will spend a little bit more time on the derivatives of logs. Our primary one, of course, is natural log. We use natural log for most things, but then we want to try to get into logarithmic differentiation, which is really the implicit differentiation with one step added at the beginning, which is to take the natural log of both sides and then apply implicit differentiation. So what we're going to start with here is the derivative of an exponential function. So we're looking here. Most of the proofs for these derivatives are really way beyond the level of a Calculus 1 course. To be honest with you, they're beyond the level of a Cal 2 or a Cal 3 course. They're really a real analysis level course, which is a junior level course for math majors only. So it is a quite difficult proof, and so we're not going to go into them. You're simply going to have to accept the definitions. One of the definitions of Euler's number E, that 2.71828182845, it is not a repeating pattern, it's irrational, is that it is the unique value greater than 0, the unique positive number, where the derivative of the exponential of it at 0 is 1, all right? So what it's talking about is that on the curve of e to the x, which is an exponential function, which has this basic shape, right? Approaches the y-axis going to negative infinity, shoots off towards infinity as it goes to the right very quickly. This is how population spreads. This is how diseases spread. This is how COVID went, right? You know, at first you just had a couple people sick, not too many, then more, and then all of a sudden it just went right and went around the world like crazy. Wildfire, exponential function. E to the x is the unique base where the derivative here at the point 0, 1 is 1. So at the point 0, 1, we have the slope of the tangent line is equal to 1. And so that gives us the equation y minus 1 equal to 1 times x minus 0, which gives us y minus 1 equal x, or y equal x plus 1. That's where they came up with the equation of this tangent line. So that's what Euler's number is. It's another way of defining it. You'll find in Calculus 2 another way of defining it, actually 2 ways of defining Euler's number. There are multiple ways of defining it. One of them is as the limit as x goes to 0 of 1 plus 1 over x to the x power. That's one of them. All right, gives us 1 to the infinity power. I think I said that right. 1 plus 1 over x, maybe to the 1 over x power. Yeah, to the 1 over x power. That's one definition. And another one is using sequences in series. All right. And then based on that number e, we define the logarithm of base e of x to be the natural log of x. E as a base is a natural number to use as the base. It's the best base to describe the growth of population, viral spread, the spread of like an oil spill, anything like that. These things tend to be exponential. They spread like crazy, all right? So when we're looking at them, they can also describe the decay of radioactive material, that sort of thing, the growth of money and continuously compounded accounts, all those sorts of things. We're not going to go through the derivation of the derivative of b to the x. I'm simply going to give you the derivative of it, but you can find it in here and it goes through the properties of it. But basically the derivative of e to the u is e to the u times the derivative of u with respect to x. So the derivative of e to the x is itself. That's why e to the x, or why e makes a natural base. if the base were 5, it were 5 to the x, then the derivative would be 5 to the x, but it would also carry a factor of the natural log of 5. So it carries the natural log of the base. So that's the next thing we want to take a look at. When we're looking at the derivative with respect to x of b to the x, the formula is b to the x natural log of the base. And if we're taking the derivative of a composed function where the power is more than just x, we get b to the x natural log of the base, or b to the u rather, b to the u natural log of the base times the derivative of u with respect to x. Now you may be wondering, if that's the rule where you have a natural log of the base, where's the natural log of e? Well, it is here, but who remembers from algebra what is the value of the natural log of e?
Isn't it 1?
It is 1. And so it disappears, or rather it gets absorbed into everything else, because the natural log of e is simply equal to 1. So the rule is the derivative of b to the u is b to the u times the natural log of the base, whatever it is, times the derivative of the original power. Now that's the chain rule built into it, and this is part of the formula. But for e, as the natural base, that natural log of base goes away because the natural log of e is 1. That's why it is the natural base, because it is an easier formula, basically. We call it the natural base because the formulas are easier. You should memorize this form right here in case b is not e, and you should memorize this form right here. Those are the two that you need to commit to memory. All right, so let's take a look at a simple problem. We have x e to the 2x. All right, so x e to the 2x is going to give us the product rule. So we have x times e to the 2x. E to the 2x is chain rule. So we apply product rule first. F prime is 1 times g e to the 2x plus g prime, which is going to be e to the 2x, natural log of e, times the derivative of 2x, and I'm writing this out longhand, and then times f, which is x. So this gives me e to the 2x plus e to the 2x, natural log of e goes to 1, the derivative of 2x is 2 times x, or I would write e to the 2x plus 2x e to the 2x. Now you will often in textbooks and in web work see that they factor off the exponential. And let me talk just a second about why we do this, why this is a typical thing to do. If you have an exponential, remember the form of the exponential. It looks like this, right? It approaches the y-axis as it goes to negative infinity, and it approaches infinity as it goes to the right towards positive infinity. It never touches the x-axis. It has no x-intercepts. It is never equal to 0. So because it is never equal to 0, we often factor it off because we're often looking for where it is equal to 0, and that would be where 1 plus 2x is equal to 0. So when we use these, we're often looking for solutions where it's equal to 0. So we factor exponentials out because they're never 0. That's basically what the rule is. Okay. All right, let's take a look now at the next part, which is a mosquito population. We have A of t equal to the 1000 e to the 0.3 t. And we're looking at this one, and it's describing the population after t days, and we want to know what is the rate of change after 4 days. So rate of change, this phrase right here means derivative. So we want to find dA dt, not x, because it doesn't have an x in it, it has t. So we're going to find the derivative with respect to t of 1000 e to the 0.3 t. So when we take the derivative, this is an exponential. So the derivative, the constant just tacks along. We get the derivative of the exponential is the exponential times the natural log of e, which is 1, times the derivative of the power, which is 0.3, right? When we multiply that out, we end up with 300 e to the 0.3 t. And now we're asked to find what's the change in the amount of mosquitoes after 4 days. So when t equal 4, what's the change in the growth of the population or decline of the population? So we put in 4 and we get 300 times e to the 1.2, which turns out to be roughly 996. What does that mean? That means that it is growing by 996 mosquitoes each day. So the amount is changing by 996 at a time, right? One at a time. Okay, let's take a look now at the next part, which is, I think, another example, or no, this is the derivative of b to the x, which we've already covered. The derivative of b to the u is b to the u natural log of b du dx. So we've already covered that. So let's find the derivative of this problem here, where we have x squared e to the x. So the derivative is going to invoke product rule. So we have derivative of x squared is 2x times e to the x, plus derivative of e to the x is e to the x natural log of e, which goes to 1. Derivative of x is 1 times x squared. So we get 2x e to the x plus x squared e to the x. And you'll often find in textbooks, they'll factor out the e to the x because they're trying to find solutions where it's equal to 0, and exponentials are never equal to 0. All right, that can't ever happen. All right. Let's take a look now at the next one. I'm missing. All right. All right, let's take a look at the next one, which is e to the negative x over x. Now, you can do this a couple of different ways. You can do this with the quotient rule, or you could do this with the product rule. Quotient rule would apply to e to the negative x over x. Product rule, you would instead rewrite it so that you had e to the negative x times x to the negative 1. So you could do it either way, you'll get the same solution. So if I did the quotient rule, it would be f prime, derivative of the numerator, e to the negative x, natural log of e, which goes to 1, times derivative of negative x, which is a negative 1, times the denominator, minus derivative of the denominator is 1, times the numerator, e to the negative x, all divided by the denominator squared. So this will give me a negative x, e to the negative x, minus e to the negative x over x squared, right? You could do it as product rule as well, and it would work out. You would have f prime g plus g prime f. So f prime would give you e to the negative x, natural log of e goes to 1, times negative 1, derivative of the power, times x to the negative 1, plus derivative of x to the -1 is negative x to the -2 times the first e to the -x. Then I could move the x to the negative powers to the denominator, and this would give me, let me create some more space in here. Oh, I can't create more space because of the way I typed it in. All right, so this would give me negative e to the -x over x plus, or no, minus e to the -x over x squared. And if I got a common denominator, I would get negative x e to the -x minus e to the -x over x squared, which is identical to what I got doing the quotient rule. Okay.
I have a question.
Okay, what's your question, Juan?
Oh, why do you have negative x to the e to the negative x? Why? Like you put natural log of -1. Like where
Up
does
here?
Yeah, like in the final solution we get negative x e to the -x. I don't.
This part.
Yeah,
Okay.
that part.
All
That
right.
negative.
So this is coming from the derivative of the numerator. So this e to the -x is the exponential again, natural log of the base, and then derivative of the power. This is the du dx. The derivative of the power is a -1. All right. Derivative of -x is -1. This x is coming from the denominator.
Oh, okay, I got confused because they were close. So I thought
They're close, but
Yeah,
they're
they're
not.
not.
Yeah, this
Yeah.
x is coming from the denominator. So this is my f prime, this is my g, and this is my g prime, and this is my f. We're going to take a look at f of x equal to the square root of e to the 2x plus 2x. So remember, we have a composed function. On the outside, we have the square root of x. That's our outside function. And e to the 2x plus 2x, that's our inside function. All right. So when we look at the outside function, to take the derivative, we take 1 over 2 the square root, freeze the inside at e to the 2x plus 2x, and then we multiply by the derivative of the inside. Now the derivative of e to the 2x is going to be e to the 2x times the natural log of e, which goes to 1, times the derivative of 2x, which is 2. Then we have the derivative of the 2x term that was under the radical, which is just going to be a 2. So we get a plus 2. And all of this is being multiplied by that fraction. So we've got a 2 in common between the numerator and the denominator. We can write this as 2e to the 2x plus 2 over 2, the radical of e to the 2x plus 2. We could factor the 2 out of the numerator, and that would give us e to the 2x plus 1 over 2 times the square root of e to the 2x plus 2x. I lost my x. I knew something was wrong. And then the 2's would cancel, right? And that's simply the formula for the derivative, all right? The next one is actually a special function. It has a name. This is actually something called tanh, all right? It is a hyperbolic function. So this is actually hyperbolic tangent, and we pronounce it tanh of x. And so this is the hyperbolic tangent function, which, believe it or not, is not actually related to trig. It's related to exponentials. And the formula is the hyperbolic sine divided by hyperbolic cosine. And that's where we get the e to the x minus e to the minus x over e to the x plus e to the minus x. That's hyperbolic sine over hyperbolic cosine. But to do the derivative, we're simply going to do the quotient rule. So we're going to take the derivative of the numerator, which is going to give us e to the x minus e to the minus x times -1. That's derivative of e to the u times the derivative of the power u. Derivative of negative x is -1. And then we multiply this by the denominator, which is e to the x plus e to the minus x. And then we subtract the derivative of the denominator, which is going to be e to the x plus e to the minus x times -1, then multiplied by the numerator, which is e to the x minus e to the minus x. And all divided by e to the x plus e to the minus x squared. Now, multiplying out these powers can be really tricky, and you want to be kind of careful with it, because what you've got here is you've got to do the basically FOIL. And remember, when the bases are the same, you can add the powers. So e to the x times e to the x gives me e to the x plus x, which is e to the 2x, all right? On the outside, I get e to the x plus e to the negative x. X plus negative x is 0. What would e to the 0 be equal to? Just 1, right? And that's from the outside. On the inside, I had a -1 times the negative e to the negative x. So now it's a positive e to the negative x times e to the x, which gives me another e to the 0 on the inside, which is also 1. And then the last term gives me e to the negative x times e to the negative x, which is e to the negative 2x. And then I'm going to do the second part all in 2 steps. I'm going to leave the negative on the outside for now, and I'll do that in just a moment. So I have e to the x times e to the x, which is e to the 2x. You add the powers. X plus x is 2x. On the outside, I have e to the x times a negative e to the negative x. So I get a negative e to the 0. X minus x is 0. So I get a minus e to the 0, which of course goes to -1. On the inside, I also have another negative e to the negative x times e to the x, which gives me another negative e to the 0, which goes to -1. And then the last one is going to be a negative, that is a negative x, right? Yeah. Okay, and then the last one is going to give me e to the negative 2x, negative e to the negative 2x, right? And this is all over the denominator squared, which we can just write like that and leave it in simplified form. And I wish I could distribute this out and create some more space, but I cannot, right? So if I put in the sign, I've got an e to the 2x and a minus e to the 2x. So those are going to cancel and disappear. So I can go ahead and cancel those two out. That is going to cancel that one. I've got a +2, but then I've got a -2, but it's a -2, which is actually going to give me 2 plus 2, which is going to give me like a 4. So I'm going to have a 2 here, and then I'm going to have a minus a -2, which is going to give me another 2. Then I've got e to the -2x, and I've got a minus e to the -2x, which is another plus e to the -2x. So that's going to give me a plus 2e to the -4x. Let's make sure I haven't messed something up. Something seems off. The last one should be positive. That's what's wrong. I missed a sign up here. So when we're doing the first times the first, we get e to the 2x. The outside is a negative e to the 0. The inside is another negative e to the 0, but the last one is a negative times a negative, so this should be a plus. And now those two will cancel because I'll have an e to the negative 2x here minus e to the negative 2x, so they cancel out. I knew there should be cancellation. So that one will cancel that one. So basically we end up with 2 minus a negative 2, all divided by the denominator squared, which is equal to 4 over e to the x plus e to the negative x quantity squared. This is actually the hyperbolic secant squared. All right, so it gives us hyperbolic secant squared. Okay. All right, which I don't expect you to know that it's hyperbolic, but just for funsies, I'll put that in there. This actually describes the shape of a wire suspended from 2 telephone poles. All right, so that's a hyperbolic function. Okay, are there any questions on that one? That one is a super hard one. All right, lots of algebra going on in there with the exponentials. If we had more space, it would be better. I need to redo this page and create a lot more space. Okay.
I think like every time we talk about the derivative of e, every time you go through it, I'm like, where'd the 1 come from?
Yeah.
I'll probably have to study that again.
Yeah. Yeah. All right. Let's look at the next one, which is actually easier. This will be an easier problem. We have 10 to the x over the natural log of 10. Now, the natural log of 10 is actually a constant. It is a number like 5, all right? So if we want to, we could rewrite this one as 1 over the natural log of 10 times 10 to the x. And we can think of this as just being a constant. So when we take the derivative of it, f prime of x, we're taking the derivative really of the 10 to the x, and the 1 over the natural log of 10 just follows along as a constant factor. So the derivative of 10 to the x is going to be 10 to the x, natural log of the base, which is 10, times the derivative of the power, which is 1. So this is going to give me 1 over the natural log of 10 times 10 to the x times the natural log of 10. So the natural logs of 10 cancel, and I just get 10 to the x for the solution. All right, because the natural logs of 10 canceled. Right, remember natural log of 10 is a constant. It's an irrational number, it goes forever. Right, and remember, if the base of the exponential is not e, then you have to do the natural log of the base, and so you get that part in there. Let's take a look at 3 to the sine of 3x. So we're looking at the derivative of 3 to the sine of 3x. So that's 3 to the u. So we can think of this as 3 to the u. So the derivative is going to be 3 to the u, natural log of 3, times the derivative of u with respect to x. That's the chain rule built into it. So this is going to give us 3 to the sine of 3x times the natural log of the base, which was not e, so it didn't go to 1, times the derivative of u, which is the power sine of 3x. So the derivative of sine is cosine. Freeze the inside at 3x, then multiply by the derivative of 3x, which is 3. All right, so let me pause there and make sure you're following. So 3 to the u is the 3 to the sine of 3x, natural log of the base, which is 3. Then derivative of the power is the du dx. So derivative of sine gives me cosine, freeze the same inside, times the derivative of 3x, which is 3. This will give me a 3 times the natural log of 3 times the cosine of 3x times 3 to the sine of 3x. Right? Now, you can do one more thing algebraically. It's not required, but it is possible. You have a 3 to the first power and a 3 to the sine of 3x. Because they have the same base, 3, you can add the powers. So you could actually write this as the natural log of 3 times the cosine of 3x times 3 raised to the sine of 3x plus 1 power. All right. So that means 3 to the sine of 3x plus another 3 to the first multiplied in there. Again, the last step is not required. It's just an algebraic simplification. The factor 3 multiplied by 3 to another power gives you 3 to the 2 powers added together. That's just a basic rule for algebra. Let's look at this next one, which I think is actually the last one in this section. This is actually a relatively straightforward one, but it does have the product rule a couple of times. X to the pi is a power rule. So this one is going to be done with the power rule because pi is a constant. So it is not the exponential rule. But pi to the x, this is going to be the exponential rule because the base is a constant and the power is the variable. So that's the difference. You use the power rule when the variable is in the base and the power is constant. Use the exponential rule when the base is constant and the power is variable. So let me write that over here. This is a variable to a constant power. And this is constant to a variable power, right? So the exponential rule and the power rule apply to different situations. We've got the two multiplied together. So I'm going to think of the first one as f and the second one as g. So f prime is going to give me the derivative of x to the pi, apply the power rule, pi x to the pi minus 1, that's power rule, times the second function, pi to the x power, plus, now I need the derivative of pi to the x, which is the exponential rule. So that's going to be the exponential again, pi to the x, natural log of the base, which is pi, times the derivative of the power, which is just 1 because it's x. And then I multiply that by the first factor, x to the pi. So this is like my f prime g plus g prime, and this is f from the formula for the product rule, right? Where I'm using f twice, but to mean different things. And then I can simplify this maybe a little, but not really a lot. I do have pi twice here as a factor, pi to the first power and pi to the x. So I could write this as pi to the x plus 1 power times x to the pi minus 1 power. And then on the next part, I really can't do anything to simplify this. I have pi to the x power, x to the pi power, and then the natural log of pi. And there's really nothing I can do to simplify that. It simply stays. Let's talk about the derivative of a natural log function or a logarithm. Derivative of the natural log is 1 over x. So the derivative of natural log of x is 1 over x. The derivative of the natural log of u is 1 over u du dx. So the form I want you to memorize is this one right here. Now you may ask, of course, what do you do if the base is not e? Natural log assumes that the base is e. So what do you do if the base is not e? Well, if you have the derivative with respect to x of the log base b of u, this becomes 1 over u times the natural log of the base. So you have that natural log of the base again, times du dx, right? But this time, because the formula is in the denominator, then the natural log of the base also goes in the denominator. And of course, this does have a natural log of e in it, but the natural log of e is 1, so it cancels out, or rather gets absorbed into the rest of the expression. So the derivative of natural log is 1 over u, derivative of the inside du dx. Derivative of a log with a base other than e is 1 over u natural log of the base du dx, derivative of the argument to the log function. All right, we can go through the proof of it pretty easily. If we start with y equal to the natural log of x, we can convert from natural log form to exponential form. The base is e. When we write ln, the base is e. The power is y, and the answer part is x. So we have e to the y equal x. This is the equivalent exponential form to the logarithmic form. Then we take the derivative of both sides. Derivative of e to the y is e to the y dy dx. Remember, we have to put the dy dx because we have a y there and it's not an x. And the derivative of x with respect to x is just 1. After this, we're going to solve for dy dx. This is basically implicit differentiation is what we're doing. We solve for dy dx by dividing both sides by e to the y. But we have e to the y up here in the second line. We know that e to the y is equal to x, so I can replace e to the y with x. And I have the derivative of y with respect to x is 1 over x. And this is the explicit formula for it. All right. It can also be derived from the formula for the inverse function, 1 over f prime of f inverse of x, by doing 1 over the derivative of e to the u is e to the u. The inverse of e to the u is natural log of u, and e to the natural log of x is x. So it also works in applying that inverse function for the derivative, all right? We do want to memorize the u form. This one comes up a lot in calculus. So you're going to see this a great deal in calculus 2 and calculus 3. Natural logs are a normal part of chemistry when you're talking about the pH of an acid or the alkalinity of a base. You get this pH scale, which is a logarithmic scale. When you're talking about earthquakes are logarithmic scales. The typical Richter scale is based on base 10, so that if you have a magnitude 6 quake compared to a magnitude 5 quake, it's a difference of 1, which is actually a power of 10, 10 to the first. So a magnitude 6 is 10 times more powerful than a magnitude 5, all right? Which is why they sometimes talk about a 5.5. A 5.5 is 1 time more powerful than a 5.4. All right. So when we're looking at this one, we're going to remember that the derivative with respect to x of the natural log of u is equal to 1 over u, technically natural log of the base, times the derivative of u with respect to x. In our case, we're going to have that f prime is 1 over the inside, which is 3x plus 2 to the 5th, times the natural log of e, which of course goes to 1, times the derivative of the inside, which is chain rule, because we've got the 5th power. So we have 5 times something to the 4th, freeze the inside at 3x plus 2. then multiplied by its inside, which is 3. So it's very much like unraveling a very tangled knot. So we have 1 over u, natural log of the base, times derivative of the inside. This is chain rule again. 5 times something to the 4th frees the inside, derivative of the inside of the chain rule, which is 3. Right? Then we can multiply the 5 and the 3 together. That gives us 15 times 3x plus 2 to the 4th power over 3x plus 2 to the 5th power. There's cancellation here. These 4 cancel all but one of those. So we have 15 over 3x plus 2. Because of the addition, that denominator is a group. All of it goes or none of it goes. You cannot cancel the 3 with the 15 because it's not a 3 by itself. It's a 3x plus 2 group. All right. Let's take a look at the next one, which is the natural log of 4x cubed plus x. And again, the derivative with respect to x of the natural log of u is 1 over u, natural log of the base, times du dx. All right. So we're going to have instead f prime equal 1 over u, the argument to the natural log, just as it is, times the natural log of e, which goes to 1, so we don't actually have to write it, times the derivative of the inside, which is 4x cubed plus x. So the derivative of 4x cubed is 12x squared plus 1. So we can write this as 12x squared plus 1 over 4x cubed plus x. Because of the addition in each part, there are groups. I could factor the x out of the denominator group because it is common to both terms, but I don't have a common x on top. So there's really no advantage to doing that. I'd probably just leave it. Okay. Let's look at this one. So I'll write the derivative rules up here so that you can remember. The derivative of e to the u is e to the u, natural log of e times du dx. The derivative with respect to x of natural log of u is 1 over u, natural log of e, times du dx. All right? So in this one, we have e to the x cubed times natural log of x. So we have an e to the u, but within the e to the u, we have a product rule. And inside the product rule, we have a natural log. All right. And I'll show you a couple of ways of attacking this problem. There are actually 2 decent ways of attacking it that make sense. One is to do it directly. So we can have f prime equal to the derivative of e to the u is e to the u, so the formula remains unchanged, times the natural log of the base, which goes to 1, times the derivative of the power. The power I'm going to think of as x cubed times the natural log of x. So the derivative of x cubed is 3x squared. So this gives me 3x squared times natural log of x, product rule, f prime g, plus g prime f. Derivative of natural log of x is 1 over x. The natural log of e is 1, and the derivative of x is 1. So I just get 1 over x times x cubed. All right, that's my g prime f. Okay. So I've done e to the u, natural log of the base, derivative of u with respect to x. Right. Now I can clean this up a little bit, and I can write this as e to the x cubed, natural log of x, times 3x squared, natural log of x, plus x squared, right? And you could leave it like this. There is some simplification, but it's really hidden. It's sort of hidden. I'm going to show you another way of attacking this algebraically that will probably simplify the result. So let's take a look at doing this using some simplification before we start. So this is an algebra rule. We have e to the x cubed times the natural log of x. It occurs to me that if I have these two together, when I get to the answer down here at the end, let's see, could I split it up? I could. Remember, there is a rule that says that if you have a factor on the natural log, that factor becomes a power on the answer part. So I can pull this x cubed into the natural log as the power on x. So I can rewrite this as x to the natural log of x to the x cubed function. This is what's called a tower function. We have not seen these before. This is brand new. This is a variable base to a variable power. It's called a tower function. It is the fastest growing class of functions that we study in calculus. They grow incredibly fast. They make exponentials look like lines. They make them look like they're growing so slow. They grow incredibly fast. Now, what's the advantage to writing it like this? This gets the e and the natural log back to back and touching each other. And once they're touching each other, these are inverse functions. They undo each other. And this actually reduces and gives you x to the x cubed, right?
Is it written? It's hard to tell. Is it e raised to natural log of x
Yes,
raised?
it is. This is the power. So that's a power on the e. E is the base and the power is natural log of x, and the power on x is x cubed. So we have multiple levels here. So this gives me x to the x cubed. All right. Now, this is very difficult to take the derivative of, which is one reason we leave it in this form up here. But the reason I write this here is when I get to the end down here, I could represent this factor that's at the front, this e to the x cubed natural log of x, as x to the x cubed. So that I could write the derivative of the whole thing then as x to the third. It really is a power on the base, multiplied by 3x squared natural log of x plus x squared. So it's a tower function. We think of it as building on the base, right? So we have a power on a power. So it really is, the 3 is the power on x, the x cubed is the power on that x. All right, and that would be another way of writing the solution. Let's look at one more. We have x squared natural log of 9x. Remember that the derivative with respect to x of the natural log of u is 1 over u natural log of the base times du dx. And the natural log of e, of course, goes to 1. So it's 1 over u du dx. So when we look at our natural log of 9x, the u is 9x. That's the inside of the natural log. We have a product here between x squared and the natural log. So first we take the derivative of x squared, which is 2x, and multiply by the natural log of 9x. Plus, now we'll take the derivative of natural log of 9x, 1 over 9x, derivative of natural log of e is 0. Let me say that again. The natural log of e is 1. There we go. So it goes away. And then we have the derivative of 9x, which is 9. And then we multiply by the first factor, which is x squared. All right. So this is our 1 over u. This is our du dx. And this is our f. So we have f prime g plus g prime f. When we simplify, we get 2x natural log of quantity 9x plus the 9's cancel. x squared over x reduces to x. Right? And I can write it like that. Now, algebraically, there are other things you could do. You could lift the power 2x at the front on top of the 9x. I don't know that it's an advantage. You can also split up the 9 and the x, right? The limit of the natural log of a product is the sum of the natural logs. So we could do that, but it's not necessary. We can simply leave it like this. All right. I've already talked about this rule, and I'm not going to go through the proof of it. So let's continue with example 8. We have a log of secant of x. Now, it did not write the base, but if it writes out log, the base is understood to be the common log, which is what we use for the Richter scale for earthquakes, base 10. So we have base 10 log, and then the argument to it is secant of x, right? So our derivative rule, when we apply it to the log base b of u, is 1 over u, natural log of the base, times du dx. So f prime becomes 1 over the argument, secant of x, times the natural log of 10. Since the base wasn't e, it doesn't go to 1. It's just the natural log of the base, which is 10, times the derivative of secant, which is secant of x, tangent of x. And the derivative of secant of x, tangent of x, the secants would cancel. And we could write this as 1 over the natural log of 10, which is a constant, times the tangent of x. Or you could put it in the numerator of the fraction, whichever you prefer. Okay. Let's take a look at example 9. So again, we have the derivative with respect to x of the log base b of u is equal to 1 over u, natural log of the base, times du dx. So f prime becomes 1 over the argument to the log function, which is 6x to the 4th plus 3, quantity to the 5th. Then we multiply by the natural log of the base. The base is 7. If it were e, it would become a 1 and disappear, but it's not e, it's 7. So we get the natural log of 7. And then we multiply by the derivative with respect to x of the argument, which is 6x to the 4th plus 3 to the 5th. That will invoke chain rule. So the 5 comes to the front, freeze the inside, leave the power as 4. So this becomes 1 over 6x to the 4th plus 3 to the 5th, natural log of 7, times 5, 6x to the 4th plus 3 to the 4th power, times the derivative of its inside, which is 6x to the 4th plus 3. So it's like an onion that you're peeling the layers off from the outside to the inside. First, you attack the log with the 1 over u natural log of the base. Then you attack the inside, which has a power. So you do the power rule. And then you attack the inside of the power, which is 6x to the 4th plus 3, which gives you 24x cubed. Now the 6x to the 4th plus 3 cancels with the 6x to the 4th plus 3 in the denominator. And we end up with, what is 5 times 24? Is that 120? I believe 120x cubed over 6x to the 4th plus 3 times the natural log of 7, which is still there as a constant factor. We have one more to do before we can look at logarithmic differentiation. One more example. This is a product of an exponential with a logarithm. And the logarithm also has an exponential on the inside. So we're going to have product rule. And within the product rule, we'll have exponential rule and the logarithm rule. And within the logarithm rule, we'll have chain rule with another derivative of an exponential. So I'm going to think of the 2x as f and the log base 3 of 7x squared minus 4 as g. So this becomes f prime, different f, not the same as the original. So f prime, derivative of e to the u is e to the u times the natural log of the base 2 times derivative of the power 1 times log base 3 of 7 to the x squared minus 4 power. So this is my g. Plus, now I need g prime. So the derivative of log base 3 is going to be 1 over the argument. So 1 over u. So we have 1 over 7 to the x squared minus 4 power times the natural log of the base, which is 7. All right. So our base is 3. Sorry, I'm looking at the wrong part. All right, we're doing the derivative of log. So the derivative of log is 1 over the u, unchanged, 1 over u, natural log of the base of the logarithm, so natural log of 3, now times du dx, derivative of the argument. So derivative of the argument is going to be, again, 7 to the x squared minus 4 times the natural log of 7 times the derivative of the power, and the derivative of x squared minus 4 would give me 2x. All of this is g prime. All of that is g prime. And then I need to multiply by f. So then I multiply by a 2 to the x power. Right? So this is a really complicated one. It's difficult because we have a mixture of exponentials and logarithms, and the logarithm has an exponential inside of it. So again, 1 over u, natural log of the base of the logarithm, times the derivative of the inside, which is the exponential, natural log of the base of the exponential, which is 7, times the derivative of the power on the exponential, which is 2x. And then we multiply by the first factor again. Are there any questions on that one? I'm going to clean it up a little bit, but there's not a lot we can do to it. Now, in the second one, I do have a 1 over 7 to the x squared minus 4. And I also have a 7 to the x squared minus 4. So those will cancel. And I'll get a natural log of 7 over the natural log of 3 with the 2x times 2 to the x. So I'll have a natural log of 7 on top times a 2x, which I probably would put at the front. Move my plus over a little bit. I have a natural log of 3 in the denominator, and I also have a 2 to the x power. Right? Notice that these exponential functions end up canceling. The 1 over u cancels because the derivative of the exponential also has e to the u, so they cancel. All right. I have given you the most difficult problems I could come up with that were reasonable to do in a classroom setting. This is not what you're normally going to get. They are not going to be this hard. They are not going to be this complicated. I've come up with very complicated ones because if you can follow the logic of what we're doing here, you will be able to handle anything I throw at you on an exam. All right, it will not be this hard. Okay,
I asked one question.
sure.
The part you sectioned off for G prime, I kind of got lost halfway through that
Okay.
portion.
Let's go
Um,
over the parts of it then, and I'll circle each part and label it. So this part right here is 1 over u. And this part right here is the natural log of the base. And then this part over here is all a part of du dx. All right. So we have 1 over u here, natural log of the base here, derivative of u. And what was u? U is the inside, which is an exponential. How do we take the derivative of an exponential? The derivative of the exponential is the exponential times the natural log of the base of the exponential times the derivative of the power of the exponential. Okay, so let me
Yeah, I get very lost when you say that.
all right, so let me circle those parts and label those parts. All right, so then I'm going to have, I will highlight this. All right, and I'm going to write it in gold. So the derivative with respect to x of e to the u is e to the u natural log of the base, or actually let's make it b to the u since it's not e. B to the u, natural log of the base, du dx. All right, so the first part that I have here is b to the u. The 7 to the x squared minus 4, all of this part right here is b to the u. And then I have the natural log of 7, which is this part here, which is the natural log of the base, that part right there. The 2x is the derivative of the power. So the derivative of the power, this 2x, is the du dx right here. That kind of covers up my writing, but I think you get the pattern of it. Okay.
So we start using this form because we have a constant raised to a power.
That's correct. We have an exponential, a constant raised to a variable power.
Okay. Messing with my head.
And again, this is a very complicated one. This is probably the hardest one in the set. And if you can follow this one, then you can probably handle anything. So I'll give you a second to write this one down and make note of everything. And then we're going to talk about what logarithmic differentiation is. And we'll go through the steps to do logarithmic differentiation. So this part down here is my final answer. And it's pretty complicated. It's not simple. Okay, let's take a look now at logarithmic differentiation. What is logarithmic differentiation? Logarithmic differentiation is really designed to handle tower functions, all right? So this is really designed to handle tower functions. Oops, I can't spell today. And tower functions, again, are a variable base raised to a variable power. All right, we have a variable in both the base and the power. This is typically what they're used to handle. And the problem is we've got our variable x in two places, so it can't be both a power function and an exponential, so we call it a tower function. So we want to take a look at that. And what we're going to be doing is we can also use it for complicated products and quotients by using logarithm rules to simplify complicated products and quotients. You'll see that this does work pretty well and makes them simple. So there are basically three places that we use them. Very long, high-powered products of polynomial type functions, or quotients of polynomials raised to high powers, or for tower functions, where we have a variable to a variable power. All right, so one of those situations is where we use logarithmic differentiation. The steps are basically the steps to implicit differentiation with one extra step at the beginning, or two extra steps. We're going to take the natural log of both sides of the equation. So we apply natural log to the left and natural log to the right. If there is a tower function, a variable to a variable power, we use the log property to bring that power down to the front using the power rules for logarithms. So let's say that I had that x to the x that I had earlier, or I think it was actually x to the x cubed. Isn't that what it was earlier on? Something like that. I can apply the natural log to this, and this will bring the x cubed to the front and give me the product of x cubed and natural log of x. What this does is it allows me to get my hands on both the x cubed and the natural log of x. It pulls them both down to the line. And then I can treat it as a product rule. So the extra step at the beginning is to take the natural log of both sides. If there's a tower function, pull the power on the power down, and then multiply it by the natural log of the inside function. What was the base of the tower function? And then we apply the rules for implicit differentiation. We take the derivative with respect to x of both sides. After we do that, we're going to isolate the dy dx terms. After we isolate the dy dx terms, we factor out the dy dx, and we divide by the coefficient of dy dx. So it's basically taking the log of both sides, pulling down powers if we can or need to, and then applying implicit differentiation. Okay, so we're going to do this first on this rather complicated quotient. We have the quotient of x plus 1 to the 10th power over 2x minus 4 to the 8th power. Now, we could do this with the quotient rule. It is fine to do it with the quotient rule. But there are times in computing where doing it with the quotient rule would actually cause more calculations to be done by the computer than doing it with logarithmic differentiation. So let me show you how logarithmic differentiation gets rid of the powers that are inside this function. So we're going to start with the original expression, which is x plus 1 to the 10th over 2x minus 4 to the 8th. We take the natural log of both sides. This is that one of the two extra steps. And we have the natural log of y on the left, and we have the natural log of a quotient on the right. Now, the next step that we're going to do is we're going to apply the logarithm properties to expand the right side as much as we can. We know that the natural log of a quotient becomes the difference of natural logs, just like the natural log of a product becomes the sum of natural logs. The logs are powers, and when you're dividing, you subtract the powers, and that's where this rule is coming from. These are powers, and you have division in the answer part, which means you need to subtract the powers. So we subtract the powers, and then we pull the power that's on top of these binomial expressions to the front. This is another logarithmic property that we're using from college algebra. So the 10 comes to the front and multiplies by the natural log of x plus 1. The 8 that was on the 2x minus 4 gets pulled to the front of the natural log and becomes minus 8 natural log of 2x minus 4. Now, this expands the expression and makes it longer, but it gets rid of the powers. We no longer have the power 10 and the power 8. We've converted it using logarithmic properties into products instead. There's another hidden one here inside the 2x minus 4. We have a common factor of 2 multiplied by x minus 2. This becomes a product, and the natural log of a product is the sum of the natural logs. So we can think of the natural log of 2 times x minus 2 as the natural log of 2 plus the natural log of x minus 2. That's the logarithm rule. When you have natural log of an answer part that is a product, it splits apart into the sum of the natural logs of each factor, right? Now, both of these get multiplied by the negative 8. So we have a negative 8 on the outside. So the negative 8 times the natural log of 2 of x minus 2 becomes negative 8 natural log of 2 minus 8 natural log of x minus 2, which is where this step right here comes from, right? So we have used logarithm properties to expand it as much as possible. Now, you may not remember all of these logarithm properties, which is why I'm going over them again slowly. You may not remember all of these rules. So again, the logarithm of a quotient becomes the difference of the logarithm of each factor. Logarithm of the numerator minus logarithm of the denominator. Logarithm of a base to a power, you pull the power to the front and multiply it by the natural log. Logarithm of a product, you split the factors and it becomes the sum of the natural log of each factor, right? So now that I have it expanded as much as possible, then I start the implicit differentiation. So I've basically added 2 steps at the beginning, apply the natural log to both sides, use natural log properties to expand the right side or the left side as much as possible, then apply implicit differentiation. So what we're doing with implicit differentiation is we take the derivative of both sides. The derivative of natural log of u becomes 1 over u du dx. So the natural log of y becomes 1 over y dy dx. If you have natural log of y, the derivative will always be 1 over y dy dx. Now, what about the derivative on the right? I said that for a computer, this makes an easier calculation, and it does. Because what we get is we get 1 over u, which is x plus 1. Natural log of e is 1. Derivative of x plus 1 is 1, and it's multiplied by 10 as a common factor. Now, the derivative of 8 natural log of 2 is 0, because that's just a constant, so it goes away and becomes 0. The derivative of negative 8 natural log of x minus 2, we get 1 over u, 1 over x minus 2, natural log of e, which is 1, multiplied by the derivative of the inside, and the derivative of x minus 2 is 1, all multiplied by the negative 8. So when we get to this step, you can see that the derivative is actually quite simple. It's getting very simple, more simple than it would if we had applied the quotient rule. The quotient rule would have lots of powers, lots of polynomial expressions, and lots of steps for the computer to calculate. You have to worry about more steps when you're programming a calculator or a computer, because the more steps it takes, the more energy it takes, and energy creates heat. And heat is bad for the inner parts of a computer and a calculator. You think I'm crazy, I'm not. When they do programming, they have to take into account the number of steps to produce the answer. They're always looking for ways of finding solutions that require fewer calculation steps, because that heats up the computer or calculator less and causes less damage to the parts. Once we get to here, then we have to multiply both sides by y, which is the same thing as dividing by the reciprocal or dividing by the coefficient. Dividing by 1 over y is the same as multiplying by y, and it moves the y to the right side. So we're again isolating our dy dx. And when we isolate dy dx, we end up with this xy times 10 over x plus 1 minus 8 over x minus 2. But I know what y is. I started with y equal this fraction. So I can replace y with this, and this is actually an explicit formula for the derivative, but it doesn't have as many powers or steps to take as it would have if I'd used the quotient rule. All right. Okay. Now, could you simplify it? Yes, you can. Is it worth it to simplify it? It depends. In this particular problem for a computer, I would say no. For a computer, you would probably leave it at this step up here, all right, the very first one, because it requires fewer steps, fewer calculations on the computer. For us, you could go through the other steps to get a common denominator or whatever you want to do and simplify it, but I don't know that it makes sense to. So when you think about simplifying, you only want to simplify if it makes sense to simplify, if it makes the result simpler and easier to use. If it doesn't, then maybe it's not worth doing. All right. So honestly, I kind of prefer this solution right here, and I would probably leave it like that. All right. Now let's take a look at the other situation where we do logarithmic differentiation. This is a tower function. We have y equals x to the x power. This is a variable to a variable power. This is a tower function. These are the fastest growing class of functions that we study in calculus. They grow unbelievably fast. It's phenomenal. I mean, I can't even describe how fast they grow, but later this semester, we'll talk about the strength or rapidity or the degree of infinity as far as how fast they grow. And this one is the fastest growing of all classes of functions we study in calculus. So when we take the derivative of this, we're going to apply the natural log first to both sides, because we have to get the x down to the line so we can get our hands on it. So we take the natural log of both sides because it's a tower function. Whenever you see a tower function, you need logarithmic differentiation. Then you apply logarithm rules to expand both sides as much as possible. Natural log of y is as simple as it gets. It doesn't get more simple. But on the right, I can pull the x that's the power on the base x out to the front and turn it into a product instead. So now I have x times the natural log of x. All right? So I have natural log of y equal x natural log of x. I've expanded it as much as I can. There's no product or quotient inside the natural log. So now I start implicit differentiation. I'm going to take the derivative of both sides. So first we do natural log of both sides. And then we expand if possible. And now we start implicit differentiation. Take the derivative with respect to x of both sides. This is going to give me 1 over y dy dx on the left. It's always going to be 1 over y dy dx when it's natural log of y. And then I apply the product rule on the right. So this is going to give me 1 times natural log of x plus 1 over x natural log of e times 1 this is 1 over u, natural log of the base, derivative of u times x. So this is my f prime g. All of this is g prime f. Right? Now I'm going to clean that up a little bit. And I'm going to write this, I'm going to simplify the two sides. I leave the left as 1 over y dy dx, and the right becomes natural log of x. The x in the numerator and the x in the denominator cancel. The natural log of e is 1 times 1 just gives me 1. So I have natural log of x plus 1 now on the right-hand side. Now I need to isolate dy dx. Right? So the x's cancel. Natural log of e is 1. 1 is 1. So I just have plus 1. Right? So now I'm going to take and I'm going to isolate the dy dx by multiplying both sides by y. That's the same as dividing by the coefficient of dy dx. So when I multiply by y on both sides, I get dy dx equals y times the natural log of x plus 1. But I know what y is. Y is x to the x power. So I have x to the x power times the natural log of x plus 1. And that's my final expression for the derivative. Okay, let's take a look at the next property or the next example, which is another tower function. I know it's a tower function because I can see that there's an x in the base and there's an x in the power. They're inside of trig functions, but it's still a variable base to a variable power. It's a tower function. So since it's a tower function, I'm going to need to apply the natural log to both sides. This is logarithmic differentiation. So take ln both sides. So I get the natural log of y equals the natural log of the sine of x raised to the tangent of x power. And I will tell you in web work, the powers are not significantly above the base. So be very careful. If it looks like it's above, it is above. All right. So they are not significantly above. I'm trying to exaggerate it so it's clearly a power, but in web work, they don't look that way. Now we expand both sides as much as we can using logarithm properties. The right stays natural log of y. The left becomes tangent of x multiplied by the natural log of sine of x. Right? You pull the power down to the front. Right? Then it becomes a product. Right? Now we're going to apply implicit differentiation. So we take the derivative with respect to x of both sides. This gives me the derivative with respect to x of natural log of y, the derivative with respect to x of tangent of x times natural log of sine of x. This is going to be product rule on the right. On the left, it becomes 1 over y dy dx. And on the right, we get the derivative of tangent, which is secant squared of x times the natural log of sine of x as our g. Plus, now we have the derivative of natural log, which is 1 over u, 1 over sine of x. The derivative are then multiplied by natural log of e, which is 1. Then the derivative of sine of x, derivative of the inside, which is cosine of x. And then we multiply this by f, which is tangent of x. Then we simplify. One over y dy dx equals, I can't simplify the first term. It's as simple as it gets. But the second term I can. Remember that tangent is sine over cosine, and cosine over sine is cotangent. So I have cotangent times tangent, which is 1. All right, this is trigonometry. So my cosine over sine times tangent, everything cancels and I get +1. Now we need to isolate our dy dx. So we're going to isolate dy dx by multiplying both sides by y. And this gives me dy dx equal to y times secant squared of x times the natural log of sine of x plus y times 1, which is y. Now, you can either distribute it or you could have left it in parentheses. It doesn't matter. The last thing you want to do, though, is replace y with what it's equal to. And our original y was the sine of x to the tangent of x power, that tower function. So the last thing I would write is sine of x to the tangent of x power times secant squared of x, and I'm putting everything in parentheses so nothing gets inside the argument to another function by accident, plus sine of x to the tangent of x power. Okay. Example 13 is a little different in that it does ask us to find the derivative, but then it wants to know where does it have a horizontal tangent line. Well, a horizontal tangent line is when the slope of the tangent line is 0. So it's basically asking where is the derivative equal to 0. So first we find the derivative. This is another tower function. We have x to the square root of x. So this is x to the square root of x. It is a tower function. So we do need logarithmic differentiation. So we start the same way. We take the natural log of both sides, which is going to give me the natural log of y equal to the natural log of x to the square root of x power. Then we expand as much as possible using the logarithm properties for quotients, products, and powers, and we'll pull the power to the front. So we have natural log of y equal to square root of x times natural log of x. Those are our 2 additional steps. Now we do implicit differentiation. So we take the derivative of both sides with respect to x. So this will give me 1 over y dy dx on the left and a product rule on the right. The derivative of a square root is 1 over 2 the square root times the derivative of what was under the square root, which was x, and the derivative of x is just 1. And then we multiply by the second factor, which is natural log of x. Then we add to that the derivative of the second factor, natural log, which is going to be 1 over x, that's our 1 over u. The base is e, so multiplied by natural log of e is just 1, times 1 as the derivative of the inside x, derivative of x is 1, then multiplied by the first factor, which is square root of x. All right. And then we want to clean this up and simplify it if possible. So I have 1 over y dy dx equals natural log of x over 2 square root of x. Now, the square root of x over x, I can reduce. This is the 1/2 power. This is the first power. 1/2 minus 1 gives me a negative 1/2, which swaps it to the denominator. In other words, you can think of the x as the square root of x times the square root of x, and one of these cancels and leaves me with 1 over the square root of x in the denominator. I could very easily get a common denominator by multiplying this by 2 over 2. And then I could write it in a common denominator form as the natural log of x plus 2 divided by 2 over the square root of x. Now, the next thing I need to do is isolate the dy dx by multiplying both sides by y. So this gives me dy over dx is equal to y times the fraction natural log of x plus 2 over 2 square root of x. Then we replace the y with our tower function, which was x to the square root of x. And I will say that that natural log of x plus 2 is making me nervous about the plus 2 creeping inside the natural log. So I'm going to put the 2 on the beginning and write it as x to the square root of x power times 2 plus natural log of x over 2 square root of x. All right. And this is my final expression for the derivative. Now, the question was, where is this going to be 0? Where does it turn out to be 0? Basically, I can't have 0 for x because that would give me 0 to the 0, which is an indeterminate form, and would also give me 0 in the denominator. Thou shalt not divide by 0 ever, anywhere. Don't even think about it. Not allowed. So I can't let x be 0. So this isn't going to help with finding a solution for where the horizontal tangent line is. So it's got to come from the fraction where the numerator is equal to 0 only, and the denominator is not. So the slope of the tangent line is going to equal 0 when we have the numerator of that fraction equal to 0, which is basically going to be, something seems to have gone awry. Where are we? I didn't do it. Well, when would it be? And then tell me why I'm looking at my notes to see if I've made a mistake somewhere. I stopped. Why did I stop? What was coming that I knew made no sense? Well, I guess it does. It happens when the natural log of x is equal to -2. So it does. The negative made me nervous at first that I'd made a mistake. So I looked back at my notes. Everything looks good. It is correct. This is going to be when it's going to have a horizontal tangent line, when the natural log of x is equal to -2. Now you apply a logarithmic property and switch it to exponential form so you can solve for x. So the base is e, the power is -2, and it equals x. So this is going to have a horizontal tangent line whenever x is equal to -2. So let's see if Desmos can actually handle this function. I'm not sure what it will do if we put in y equals x to the square root of x. Okay, it handled it just fine. It was actually quite cooperative, which is unusual. Notice it does, I'm going to change the color because the purple is kind of disappearing into the graph. Let's make it thicker as well. All right, so when we're looking at this now, you can see that part of the graph is hugging along this axis here, along the y-axis, and then it's swooping and curving out like that. So we want to know what's happening. When do we have a horizontal tangent line? At e to the -2. which would have to be right down here somewhere, all right, at the bottom. So it must be that e to the negative 2 is about 0.1353. So I'm going to take my calculator and I'm going to put in e to the x, which is second natural log, then put in negative 2, and I get 0.135335283. That is the place. This is e to the negative 2. All right. So that is the point where we have a horizontal tangent line. All right. We have one problem left to do, which is an isotope problem looking at a half-life of approximately 12 hours. And we want to think about what happens with this particular substance. This element is called erbium. It's a real thing. These are the real values. Its half-life is 12 hours. So after 12 hours, half of it is still radioactive. And then another 12 hours, half of the half is still radioactive. So initially, there are 9 grams of the isotope present. A gram is about the weight of 2 paper clips, 2 large paper clips. And the half-life equation is the original quantity times the fraction 1/2 raised to the power t divided by the half-life. So first, we want to write the exponential function that represents doing this raised to the power. So our original function, q as a function of t, is going to be the original quantity, which is 9 grams, times the fraction 1/2 raised to the power t divided by 12. So our power is t and the half-life is 12 hours. So the power becomes t divided by 12, right? Then we want to determine the rate at which the substance is decaying in t hours. That's the derivative. So to find the derivative, we're going to take the derivative of both sides of the equation. So we're going to have the derivative of q of t is equal to the derivative of this expression. The 9 is a constant factor which carries along. It's an exponential because I have a constant base of 1/2. The variable is in the power. So it's not a tower function. I don't need logarithmic differentiation. I just need the exponential derivative. So 9 as a scalar multiple times, well, I repeat the exponential function, 1/2 to the t over 12 power, times the natural log of the base, which is 1/2, times the derivative of the power, and the power is t over 12. So this gives me a 1 over 12. And I can clean this up a little bit. 9 divided by 12 gives me 3/4. So I can write this as 3/4, the natural log of 1/2 times 1/2 raised to the t divided by 12 power. All of that is in the power. So this is the rate of change, how fast the quantity is changing with respect to time. Then we want to find the rate of decay at 4 hours. What is the rate of change of the population after 4 hours? So then I plug in 4 for my t, and I'm finding q prime of t. So this is part B, and part C becomes dq dt when t equals 4. So this is 3/4, which is a constant, times the natural log of 1/2, which is a constant, times 1/2 raised to the 4 divided by 12 power, all right, which is now a constant. 4 divided by 12 is 1/3. And when you multiply this out, you're going to get approximately a negative 0.4126 grams per hour. So this is the rate of change. This is the decay. This is the number of grams that are disappearing every hour after 4 hours. All right. 0.426 grams are disappearing after every hour. Are there any questions on this last one?
We look at the second or maybe it was the first one, the first formula you pulled from
Okay.
that. I think I fell behind.
All right, so on the first formula up here, you're simply writing the expression using Q naught, which is the original quantity. There are 9 grams of it present in the beginning. So the factor at the front, the coefficient becomes 9. For a half-life formula, the base of the exponential is always 1/2. So you get 1/2. And the power is time divided by the half-life. The half-life is 12 hours, so we have t divided by 12.
Okay, so that's kind of
It's a known formula.
it's a known formula, or it's also the starting point, I guess.
It's also the starting point.
Okay.
And then we take that and we apply the derivative rules for the derivative of an exponential. So the 9 is a constant, then the exponential to the power, natural log of the base, which was a half, times the derivative of the power, which is 1/12. And then you clean it up a little bit. And then when we plug in 4, we get that the rate of change is about 0.425 grams every hour. It's stopping being radioactive. After 4 hours, that's the rate of change. Okay. So that's the end of this section. So I'm going to stop here. And when we come back from spring break, we will be talking about related rates, which will be all word problems, which is why I wanted to finish this up before break, because when we come back from break, we have a difficult section to start off with, and it does take quite a bit of time. So I didn't want this hanging over our heads. So you want to be sure that you finish the homework for all of these sections over break. Any other questions?
So the reason why this was easier per se is because it's not the tower function.
That's
Like it's
correct.
less steps because of that.
Yep, that's correct. It did not have a variable base. The base was the constant 1/2, and that made it easier to do.